quadratics in P1. You first learned what a quadratic is, something in the form ax squared plus bx plus c. An algebraic expression in that form is a quadratic. And then we looked at the quadratic function. When you have y equals a quadratic expression, how that function looks like. Just like that, you now know what exponentials and logarithms are. Now we are going to see if this turns up in a function, how, for example, how does the graph of that function looks like? What can we learn about the function, a function when there is a log term in it or an exponential term in it, okay? So these are called, the two functions are called exponential function and logarithmic function, okay? So you put a main topic, let me go to the note. You put a main topic. Again, just like we started, how we started discussing what logarithms and exponentials are, we divided our page into two columns and we side by side discussed what they are. That we did so that we can compare and see the relationship between log and exponentials. Similarly, I'm doing the note of the exponential function and the logarithmic function side by side. We will write, we will discuss each one separately, but when you write, we will write it like this, so that once you have learned it, it's useful to have it side by side, so you know, you can see their inverse nature and things like that, okay? So put a big topic. This topic is parallel to the first topic you put on the first day we started this, okay? So it's a main topic under this chapter. So put the topic logarithmic and exponential functions, and let's see what these are. So just the topic, okay? Logarithmic and exponential functions. Do we have a, let me go, okay. Can I go back to the main screen? Do we have a new student? Did I see a new name? Netni. Hi, Netni. Okay, welcome to our class. Are you from Lyceum? That's an uncommon name, Netni. Okay. Now the thing is, let me have you, so as you can see, this is the second topic in P3. We started P3 a few weeks back. And if you look at the syllabus, this is the second topic of the P3 syllabus that we have started to do. Are you familiar with this? Or like, are you able to speak to me? If your microphone is working, I would like to have a few words with you, just to know where you are and whether you have done these, and where, you know, are you able to talk to me?
Can you hear me?
So you have, so you go to Lyceum Vattala.
Yeah.
Right. So you have done whatever the school has done, and have
you do maths from school. It's fourth subject.
Can you say that again? You are not doing maths in school. Are you doing it privately?
Yes.
I can't hear you properly. Yes? I can't hear you. Yes, yes. Are you doing it privately?
Yes, miss.
Right. Okay. Okay. Then were you going to a class before, and have you like covered up to where we are now?
I've covered up to AS, but not A2. I've just started A2 with you right now.
Okay. So this is this is P3.
P3, yeah.
Right. Okay.
A2.
Right. So you have to then get the notes of algebra. We did 2 topics in algebra. That's the first big topic in P3. So let's see how we can get you the notes from somebody in the class. Okay, maybe somebody can take pictures and send you. Okay. Thank you, Hatfi. Hatfi is volunteering to send you the oh, Hatfi's friend. Okay, to you, Netni. Okay, so please make sure you copy. You have to write it yourself. Copy the notes down, and then let me know if you have any doubts in that. Okay, so let's just try to follow the lesson from today. Okay,
Okay.
right. So going back to this, let's look at, so I'm starting with exponential function because exponentials are something that you have been familiar with from your O-levels. Logarithms is what you learned new in P3 last few weeks. So let's start with exponential function. Let me, let me see that I can do this. Let me zoom this and just let you see. Let me see, okay? Give me a moment. I'm trying to zoom this so that log functions goes out of the screen. I think that is okay. So don't pay attention to the other box, okay? So let's just look at this. So let's first discuss, then I will let you copy the note later, okay? Right, so what an exponential function is, now you know what an exponential term means in an algebraic expression. What we call an exponential term is something in the form b to a power of, some base, some number to a power of some number, like 2 to the power of 3, 5 to the power of 7. Any term like that is an exponential term, or it's a term we say written in index form. Okay? Index, exponent mean the same thing. Now, what an exponential function is something in the form y is equal to, so it's a function, y is equal to, you have this is the most basic exponential function that I have written here. You just have the exponential term. So you have some b is your base, it can be any number to the power of x. So x is the input of the function is in the power. Okay, y is the output, y is equal to some number to the power of x. So this function changes as x changes. You take, so say we choose the base to be 2. So if you think of the function y equals 2 to the power of x, as x changes, you can think of how y changes. So this is your function, the relationship between x and y. Okay, for a fixed base, that's why it's b, it's a number. For a fixed base, as you change the power, how does the whole value changes? That's your function. So two things to note here. If you just think of not in terms of a function, but if you just think of an exponential term, you know that your base can be any number, right? We don't need to impose any restrictions. Can the base be any positive number? Yes. Can we make sense of that? Yes. Can the base be a fraction? Yes. Can the base be 0? That won't give you anything, but there is nothing wrong in talking about 0 to the power of 5, right? That will be 0, but it's not interesting. So 0 you can ignore. Also 1, if you take different powers of 1, it's always 1. So that is not interesting either. But if you think of negative numbers, can you think of an exponential term with the base negative, with the base a negative number? Yes. Can you think of negative 2 to the power of 3? Does that make sense? It does. But when it comes to a function, we restrict ourselves for positive bases, and we don't take b equals 1 because that doesn't give you anything. If b is 1 here, this function is going to be y equals just 1. For whatever x, it's always 1. It's just a horizontal line then, right? Because it's y equals 1. So then it's not an exponential function. So we are only interested in b for bases greater than 0 with b not being equal to 1. Now, if you think why we do that, I think I discussed this a little bit the other day. When the base is negative, for different powers, your value of the value of your number oscillates between positive and negative. When you take a even power of a negative number, it's positive. If you take an odd power of a negative number, it's did I say it right? If you take an even power of a negative base, shall I go to the board? I'm just talking, and that doesn't help much, no, unless you. But when you see it, let me go to the board quickly. We don't need to discuss this much because it's not there in the syllabus. You just need to know the condition that b is greater than 1. But I don't want you to, just memorize rules without knowing why there is such a condition. If b is negative, that means less than 0. That means when you think of, like, say, -2 to different powers, think of different powers of -2. So -2 to the power of 1, let's take whole number powers so that it's easy to compute them. -2 to the power of 1 is -2. -2 to the power of 2 is 4. -2 to the power of 3 is -8. -2 to the power of 4 is 16. You see what my point is now. As the power number changes, I mean, whenever the power number is even, you get a positive answer. Whenever the power number is odd, like this and so on, you get a negative answer. So if you plot this graph, it's an 1 point up, 1 point down, 1 point up. It doesn't give us an interesting graph. So that's why you avoid taking, when you talk about the function, exponential function, you only talk about when the base is positive and we remove 1 from the base, base being 1, because that is not interesting either, right? So, oops. Right. So a function in the form y equals some number to the power of x is called an exponential function. This base can be any positive number except 1. Any positive number, not 0, any positive number, but not equal to 1. Okay. So that's why I say we will, we will only learn, even out of that, we will only learn when the base is greater than 1. Not when the base is a fraction. Between 0 and 1, all the numbers are fractions. We don't talk about those. Okay. So you are learning the exponential function when the base is greater than 1. 1, 1.2, any number greater than 1. So your base can be any number greater than 1. Okay. Keep that in mind. So for example, here are some examples. All these are exponential functions. Y equals 10 to the power of x, y equals 2 to the power of x, y equals e to the power of x. E is also a number like pi. It's an irrational number. It's a number that comes up naturally in natural growth processes, population growth processes. E comes up just like pi comes up when you talk about circles. It's a number that is embedded in a circle. You can think of pi like that. Just like that, E is a number that helps us to describe how certain populations grow naturally. That's why it's called, when you think of the log with the same base E, you call it natural logarithm. Right, okay. So you can take any b that is greater than 1 to the power of x. All these are exponential functions. And all these functions, when you graph them, they all have a similar shape. It's just like, that any quadratic function, however your quadratic expression is, for any quadratic function, the basic shape is a parabola. You know that. The only thing is it can move and the curvature might change, but the basic shape is this, or upside down, the parabola, upright one or upside down one. Just like that, for any exponential function, there is a basic shape. All exponential functions with base greater than 1 have this shape. Before I show you, does anyone know what's the shape of the exponential function, the graph of the exponential function? Oh, good evening, Nathan. You just joined? I thought somebody was responding
Yes,
to my
there's a
question.
bunch of black stuff boxes
Oh, wow.
around again.
Really? Okay. Let me see whether I can fix that.
Miss, try minima. If you have anything in front of your screen right now,
Yes, that's the chat
close it.
box that I just opened.
Ah, yeah.
No, that can't happen. That is happening means let me close everything that I have opened, all extra things that have. Did it improve?
No, still it's there, miss, at the bottom. There's a bottom long bar.
Yeah, that's my. Is that okay now?
No, miss.
Please move this window. Wait. I will stop share. Let me go back to the screen. Is this screen okay?
Yes, it's okay.
Okay, then now let me go back to this.
Black box.
Black
Bottom.
I wonder why that
On
is.
Wednesday, we didn't have this problem, no, miss?
Ah?
On Wednesday, this wasn't there, no?
No. This suddenly this thing happens, no? We have had this problem before time to time, isn't it? I'm trying to see whether I have other programs running in the background. There's nothing. I haven't opened anything. Oh, meeting controls. I'm sorry. Do you see the black box?
Yeah, it's still there, miss.
Still there, no?
But it's not blocking the notes, so it's okay.
Okay, shall we just keep going, and let's see whether it improves. Okay. Right. So, does anyone know the shape of the graph of an exponential function? Can you try to? Okay, let's see. Somebody's saying something. Like a reflected C, almost a C, not like the exact C. I think you get it. Reflected C. So like this way, almost a C, not like the exact C. So C is like that. So reflected C means like that. Yeah. I think you're close. It's not a C. Okay, this is how the exponential function, the graph of the exponential function looks like. This is moving slow. Is there a lag in the screen?
Yeah, there's a lag from time to time.
Yeah, okay. Do you see the graph now?
Yes, miss, I can see the graph.
Okay, right?
But the black box is covering. Okay, the black box is gone. Black box is gone.
Okay, that's because I don't have the black boxes come whenever I open. Like if I open the chat box, that box appears to you as a black box. If I have my status bar at the bottom coming up, it appears to you as a black rectangle. So when there is nothing, you won't see anything. Right, so this is the shape of any exponential graph. I have marked two important points that you can verify for yourselves that these points do lie on this line. That is the point when x equals 0, because whatever your base is, if you put 0 for x, whatever to the power of 0 is 1. So 0, 1 point must be on this curve. So that's one point. The other point is when x is 1, whatever your b, your base, to the power of 1 is b itself. So 1 comma b is a point on this graph. Okay, so this is how it goes, and this is what people usually refer to as an exponential growth. I'm sure you have heard of people using this term when they are talking about something that is growing rapidly. If you check out the slope of this graph, it begins with a very shallow steepness, but as x increases, it starts growing or increasing more and more and more rapidly. But something you have to note here is that this curvature never becomes vertical. The slope keeps increasing and increasing and increasing and increasing. There is always a slope. It's never, it never be, you might think because it's growing so fast, finally this will like go like that and maybe bend. No, that doesn't happen. That's when, then it will be an inverted C, like Hatti said. This is not a C, it's like that, that's all. And it's going like that forever. Okay, and if you check out this side, it looks like that the graph is like touching the x-axis. It never touches the x-axis. It keeps approaching and approaching, getting closer and closer to the x-axis. If you zoom this graph, you will see they are not touching. Okay, but it gets closer and closer and closer to x, never touches it, therefore never crosses it and goes to the bottom side. Okay, so that's the shape of any exponential graph. Y equals 2 to the power of x has this shape, y equals 10 to the power of x has this shape, y equals e to the power of x has this shape. When I say has this shape, the curvature changes depending on what the base is. But the basic, you know, this is that's what it is. The curvature will change depending on what the base you have taken. Okay, is that clear, or do you have any questions from this graph? Any questions from the graph? Or is the graph clear? Okay, you have dropped a message. Now, do you see a black box? Okay, it's clear. Hatfi, was this what you were referring to as an reflected C? Oh, yeah, I know. That's because I have opened the chat box. Okay, so it's not a reflected C. It never, a C means this comes back up. That never happens. This doesn't even become vertical. Okay, there is always a slope. There is always a steepness like that, and the steepness steepness increases. Okay, infinitely, and it goes up. Now, who can tell me? Okay, let me keep the graph on the screen. Can someone tell me? You can write on the chat box. What is the domain and range of this function? So since I have given you the graph, very easily just by looking at the graph, you can say what the domain is. Domain of a function is all the x values that it can take, the x coverage by the graph, in other words. Range is the y coverage, what y values are covered by this graph. So what is the domain of an exponential function, and what is the range? Can someone tell me? So now what will happen is when you drop a message in the chat box, when I open the chat box, you will see a black box. Okay, I will do it here. So, okay, wait. What's the domain? First answer this. What's the domain? X is what? X is equal to what set of numbers? What can X be? What's the X coverage by this graph? X is no, Hatfi. Look at the graph. What are the X values covered by this? Look, check out some points and think of the X coordinates of these points. Any real number, very good. For any exponential function, now this graph goes infinity that way and it goes up like that, okay? So it covers all the X values. If you think of all the points along this curve, for the X coordinate, you can have any point, okay? goes like that. This way to infinity, that way also it's going up, so it covers all the x values. I told you it never becomes vertical. If it becomes vertical, that means there is a end to the x value that it can take, but it never becomes vertical. So the domain of an exponential function, any exponential function, is all real numbers. What about the range? What are the y values covered by the by this function? Can someone else answer? Can I call out a name? Bimandi, are you here? Can you look at the graph and tell me what the range of this function is? Bimandi, if you can.
Y is greater than 0.
Very good. Y is greater than 0, and Hatfi also gave that earlier. Y is greater than 0. You don't have the equal sign. It never becomes equal to 0 because this, as I said, it never touches the x-axis. So it doesn't come to 0. So it's greater than 0. Okay, so that's the domain and range of this function. Now, so in the note, if I show you in the bottom here, I have in the note, I have left a space for you to write the domain and range. I have described how this graph is behaving as x increases, b of x, that's your y, grows faster and faster. Okay, and exponential functions are one of the fastest growing functions. The slope goes up rapidly. And if you think about how the graph behaves this way, it never touches the x-axis, but keeps approaching it. Okay. So when you copy the note, you will have to write the domain and range here. Okay, now let's go to the, do you want to copy this first and then talk about log functions? Or finish talking about log functions also and copy both of them together? Shall we copy
Finish
this?
talking about log functions.
Finish talking about, okay. Okay. Then here is your log function. Okay. So, sorry, this is very slow and okay. I hope you can see now. So what a log function is, when you have in your function equation a log term, y equals, you have a log term and x is in the log. Just like in an exponential function, you had y equals an exponential term with x in the power. Here you have a log term with x in the log term, and your base can be any number with the same restriction. Okay, only positive bases are considered. B can't be equal to 1, and for you only have bases greater than 1. You don't have fractional bases. Okay, greater than 1 basis only we discuss. So for example, you can have log base 2 to the power of x, not power, I'm sorry, log base 2 x, log base 10 x, log base 3.9x, any number greater than 1. Okay, so I have given you some examples here. I also have y equals ln x. That means log base e x. Okay, if you compare with the examples that I have given you for the exponential functions, I have given you, do you see, for the exponential function example here, 10 to the power of x, I have log base 10x. For the exponential function 2 to the power of x here, with the base 2, I have log base 2x. I've given you like corresponding exponential and log graph functions side by side, right? So what can change here is the base. You can think of any base. Your input is x, what goes into the log term, and your y, your output is that value of the log term, right? And now you already know that exponentials and logarithms are inverses. So if you think of these two functions, for a given base, for a fixed base, they are inverse functions. So already you must be able to visualize how the graph of the log function must look like. So exponential was like that. So the graph of the log function must be the reflection of this on the y equals x line. It has to come like down here. Okay, so let's see how the graph of the log function looks like. And here it is. So any log function has this basic shape. I think it's this document itself that is giving trouble because of these graphs that I have like inserted into the text boxes. That it's making the processing it slow, I think. Right. Okay. So this is the shape of the log, any log graph. Again, your base has to be greater than 1, and I have marked again two critical points that you can easily identify on this graph, which are, if you think of that other graph, I have reverted the numbers 1, 0, because you know when log any base, if you have 1, that is 0. So 1, 0 is on this line, and also log base b is 1. So b, 1 is also on this line. Okay, and if you look at how this curve behaves, that the function behaves, the slope becomes lesser and lesser as you go this way, but it never becomes horizontal. Okay, so it's not restricted, it goes like that. And this way your curve keeps approaching the y-axis but never touches it, therefore never crosses it and goes to the left side of the y-axis. Okay, so that's how in the graph of any log function looks like. Any questions from that? Now ignore the x equals 0 line. I'm just showing you that it's a these lines are called asymptotes. It's a line that the graph approaches. They are called asymptotes, and the asymptote is shown here. When you copy this later, you don't have to write that x equals 0 thing. Okay, is the graph clear to everyone? Hope it is clear. And then can you look at the graph? Oh, you can't see my thumbnail, no? I just realized it. I have been showing you with my hands. How did my thumbnail go away? Let me just see. I think it automatically minimized my thumbnail. Huh. Oh, it says minimize. Oh. Yeah. I don't know how to get my thumbnail back. It's telling me that the video thumbnails are minimized to optimize full screen video clip screen sharing. Does anyone know how to make it appear? So it's Zoom turning it off automatically for me. Okay, anyway, it's okay. Let's not waste time talking about it. But I wish you could see me, because I'm just explaining things with my hands. Okay, can you tell me what the domain and range of this function? What is the domain? What's the coverage of x? Can Joanne tell me? Joanne, are you here? Can someone tell me?
Miss,
Yes.
I got disconnected. What's this? What did I miss? I got disconnected after you finish explain about exponent functions.
Okay, Nathan. So you missed the logarithmic functions that we talked about. So I will send you the video. Okay, you have
Okay,
to
miss.
start. Okay. So what is the domain? Let's see, somebody's. Thank you, Bimandi. X is less than 0.
No, Miss, X is greater than 0.
Greater than 0, yes. It's very good, Sasindu and Nethni, yes. And Bimandi just made a mistake in typing. X is greater than 0. Your graph is on the entirely on the right-hand side of the y-axis. It covers only the positive numbers of x, right? So domain of this function is x is greater than 0. And what is the range? What y values are covered by this graph? All real numbers. Very good. Yes, all real numbers. Very nice. Okay, so that's good. So in this note, I have at the bottom of this graph, sorry, this is moving very slow. I'm sure you must be noticing like a lag on the screen. It's not a lag. It's actually happening here. It's not a lag in the data or the connection. Okay. So I have described about the graph here as x increases, the log base bx grows slower and slower. The slope becomes less steep and less steep. And the graph never touches the y-axis but keeps approaching it, right? And as you said, domain is x is greater than 0 and range is all real numbers. You have to fill it when you copy the note. So something important to remember here is this. When you have a log term like log x, x can only be a positive number because domain you said x is greater than 0. X is always positive. So only a positive number can go into a log term. If you have log x, x can be only positive numbers greater than 0. Okay, so that's something to remember. Let's now quickly copy this note and then we will simultaneously look at these two functions, the graphs of these two functions drawn on the same grid so that you can see the inverse nature of their functions. Okay, so that will be coming next. Let me zoom this out a bit so that you can start copying. Okay, so oops. Now you can like divide your page into two columns. You don't have to put the box. If you like, you can put it. Can you start copying this? So let me show you part by part. So up to here first, up till the examples. And let me know when you are done copying this part. There's a typing mistake here. Not an log function, a log function. It's called a log function. Anyone done copying?
No, miss.
Okay.
Okay, miss.
Okay. I will wait for 2 more responses. Okay, Nefni is also done. Okay, Bimandi is done. So I'm going to move the screen, go to the bottom. I hope that is okay with everyone. So let's go to the graph. Okay, this part, let me, oops, it went all the way up. Sorry about that. Okay, so from here, Now, when you copy this curve, both curves, draw it very carefully with the features that we discussed. Okay, the steepness, when you think of the exponential function graph, don't make it like vertical in the end. There is a slope still going on, and don't make it touch the x-axis. Show that it is getting closer and closer.
Miss, that means it doesn't touch the x-axis, no, Miss? It just slightly goes above it.
Yes. The
Okay.
exponential graph does not touch the x-axis, but keeps approaching it. And the log graph, that line, the curve at the bottom, it keeps approaching the y-axis, but never touches it, never reaches it.
Miss,
Yeah.
in the log function, Miss, the graph, that
Mhm.
also as it goes, it doesn't become a straight line, it keeps curving, right?
Yes, it keeps curving. It never becomes horizontal.
Okay.
It looks like it will eventually become horizontal, but it will not.
Okay, Miss.
So there is always a slope. The slope never becomes zero in the log function, because if the slope becomes zero, you are going to have a horizontal line eventually, but that doesn't happen. And then if that happens, your range is not going to be all real numbers. So it just keeps rising. The rate at which it keeps rising keeps decreasing, if you can understand what I just said. So that's what I mean by saying in the next sentence, when you copy that, you will see for the log graph, this curve is growing slower, and it's growing slower and slower, but it's growing. It's going up. But each as x increases, it grows more slower and slower.
Miss, in
Yeah.
this one, that is fx equals log what, Miss?
Which one?
Log what?
Log base b of x.
In the
There.
log base b
That's
of
base b
x.
x. Base b x. You don't need the bracket
Okay.
there. Yeah. I mean, you can put the bracket if you want. That's log
Okay.
base bx.
Miss, the first point there is 1 0, and the other one is what, Miss? The other point is
B,
0.
b comma 1. B.
Okay. Because my screen is not clear, Miss. That's right. Okay, Miss, done.
Okay. I'll wait for two more people to be done and then I will move this up. Do you see the black box now?
Yes,
Uh-huh.
we see it.
Okay. Okay, I'm checking the chat box, so you'll see a blur. Okay, so a lot of you are done. Right, okay, so the last bit, under the two graphs, copy the two sentences where I'm explaining the behavior of that curve, therefore the behavior of the function. And then you have to write the domain and range. And then in red, the last line under logarithmic graphs, logarithmic functions, you have to say this important thing that we noticed, that only for a log term, only a positive number can be taken. If you have log of some number, log 10 or log 5, that makes sense, but log -2 would not make sense. You can't have log of a negative number. Let me change that to saying, I think if I put it that way, it will be more clear. I will say you can't have log of a negative number. Same thing I'm saying in different words here. I think that is more clear. Domain of the log function is positive, means x is greater than 0, means you can't have log of a negative number. You can only have log of a positive number. We are not talking about the base, we are talking about the number that goes into the log. I keep checking the chat box to see whether you have dropped a message saying you are done. So this thing about log of a number, that log of a number, the number cannot be negative. It has to be very familiar to you, and it has to be something that you know very well, that you don't ever forget. It's just like now you are very familiar with the fact that when you have square root of a number, you know that a negative number can't go into a square root. As long as you are working with what are called real numbers, uh, what goes into a square root has to be positive. Just like that, make sure that this is something that you always remember. Log makes sense only if you are talking about log of a positive number, not a negative number. Just like you can't, it doesn't make sense to say square root of -2. You know that there is no real number for that, square root of -2. Okay, so you are done. Then here's what you have to copy next. I will straight away let you copy this. Next, I'm showing you. Now, we already talked about this. We know that logarithms and exponentials are inverse operations if you think of them as operations. And when you think of their functions, the exponential function and the logarithmic function are inverse functions of each other. And you can easily see it here when you now you all have written the domain and range of the two functions. A characteristic of inverse functions is that the domain of a function is the range of its inverse function, and the range of a function is the domain of its inverse function. And I hope you can see it clearly here. Now let me fill domain and range in this note. So under exponential functions, from the graph we see that domain is x is greater than 0, and the range is, I'll say y, y is any real number. Let me say it like that. Y is any real number. So y is, real number. And for the domain and range of the logarithmic function, you got the opposite. The domain did I write? Why is anyone not saying anything? Did I write this correctly? Domain of the exponential function is it right? So I have a fair suspicion now whether you did this right. For the exponential function, domain is all real numbers. X can be any real number. Why isn't anyone talking? X can be, I'll say can be any real number. And range,
y is greater than 0.
y is greater than 0. I mean, it's very clear in the graph, right? There's nothing, it's not any like rocket science to figure that out. So, right. And then here, for the logarithmic function,
X is greater than 0.
Is greater than 0.
Y is any
and
real
y
number.
is any real number. So you see that inverted nature of the domain and range. So here y is any real number, right? So I hope you have written it correctly. And then after this, you have to copy this. I have shown you 2 examples. I have drawn one exponential function graph and its corresponding logarithmic graph on the same grid to show you the inverse nature. They are reflections of each other. So the sentence is, since for a given base, Now that is important. For a given base, the base has to be fixed, okay? For a given base, log and exponential functions are inverses of each other. Their graphs are reflections of each other on the y equals x line. So in the first graph here on the left, I have fixed the base to 2. So y equals 2 to the power of x and y equals log base 2x are inverse functions. And on the right hand side, I have drawn y equals e to the power of x and y equals ln x. Ln x means log base e x. They are inverse functions and their graphs are reflections of each other. Can you quickly copy that also?
Miss, this is not under the table, no, miss?
Under the table. The table is over there. So there we have written the two functions separately.
Yeah, miss, what I'm trying to say
Under
is
under the table.
this is after the table now.
After
This is
the table.
separate.
Separate.
Ah,
yes.
okay. Okay. I'll write the whole
That's
thing.
how it looks like here in the note.
Okay, miss.
Now, when you draw the two curves, notice how the exponential curve crosses the y-axis at 1 and how the logarithmic curve crosses the x-axis at 1. You're done. Okay.
No.
No? Done?
No.
Okay.
Done.
Okay. I hope everyone is done. Right? So let me go to, okay. So this is all that you have for exponential and logarithmic functions. You have to know the shape and that they are inverse functions, how they are reflections of each other. And like if you are given a simple transformation of any of these functions, you have to know how the graph will look like a shift to the left, a shift up. If I multiply the function by a negative number, what happens? All that you have to know. You remember function transformations, right? So these basic transformations can be done on these two functions. And if you see a function, a log function or an exponential function with a little transformation happening to them, you have to know how their graph looks like. Okay. Right. Our next topic under logarithmic and exponential functions is what we are going to be looking at next is how to solve exponential and logarithmic equations. So let me see. I will close that document. I think that is what gave us trouble because of these graphs on that. Okay. Hopefully now that appearing of black boxes must not happen. Hopefully. Let's see. Okay. So your next topic is next big topic parallel to logarithmic and exponential functions. Parallel to that, a big topic, main topic is solving exponential and logarithmic equations. Oh,
Wait, Miss?
I will write it. Yes.
Miss, is it like a main topic?
It is a main topic. Let me
okay.
Let me show you. Let me write it in a Word document. Wait, I will show you. I will show you. Still the video thumbnail is minimized. I don't know. Okay. So it looks like this seeing the appearing of black boxes will keep happening. Let me change this to this and one. Sorry. So it is solving. We'll start with solving exponential and logarithmic equations. Okay, under that, let's see how to solving exponential equations. Subtopic. Okay. I'm sorry that I can't enable my thumbnail. I know you can't see me. I don't like that. Usually when I explain something, I want you to see me because I animate things with my hands, and I know that helps to understand. So what I'm going to do is, let me try going to the board. Will my thumbnail work in the board? Still no, right? Okay, anyway. So we are going to see how to solve an exponential equation, right? What is called an exponential equation. Now we have learned how to solve so many different types of equations. If I remind you, in your O levels, okay, let me see, someone is saying something. Oh, really? Hatvi can see me. Can others see me too?
Yes, can see you, miss.
Ah. But it's giving me a message saying that my video thumbnail has been switched off to minimize the whatever. Okay, I'm glad it's okay. So you can see me, right? Right. So we have learned how to solve so many different types of equations. In your O levels, if I go back uh, up to your O level time, you have learned how to solve simple equations, quadratic equations, simultaneous equations, and so on. And then in your P1, you learned how to solve trigonometric equations. And what else? I think that's all. So this is another new type of equation that you are learning how to solve, that are called exponential equation. So what is an exponential equation? You call an equation exponential when your unknown x is in the exponent. Okay. Now, if you think of a quadratic equation, like you can have x squared plus 2x and so on, right, equals 8 or something, right? Now your x here, a quadratic equation also has this index form term. Now this has an index form, but x is in the base, right? So this is a quadratic equation. But if you have your x in the power, in the exponent, it's called an exponential equation. So for example, now this is not an exponential equation, it's a quadratic equation. An exponential equation could be something like 2 to the power of x is in the exponent, is equal to 32, right? Now this is a very simple exponential equation. I'm sure you all can solve this. If I ask you to solve this, what I mean is to find the value of x so that this is true. 2 to what power is 32? So if I ask you to solve this, because it's a very simple exponential equation, you can very easily solve it. What is x equal to? You don't even have to do anything. It's just a matter of thinking. Let me see, 2 to what power is 32? 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So it's 2 to the power of 5. So I mean, you can say on this side to the power of x, you know that 32 can be written as 2 to the power of 5, right? That means x must be equal to 5. Okay, that's very easy. So there can be very easy exponential equations like this that are quite straightforward and you can easily solve. But we are going to also look at, in addition to these simple types, we are going to be looking at exponential equations where, for example, if I write something like 2 to the power of x plus 2 to the power of x plus 3. I am not sure whether you can solve this, but something like that. Now, how do we do it? right? So the difficulty level, this is very easy. These are very easy. We are going to look at some equations that are more difficult than this very simple type. Okay. So let's first write what a I can't seem to. Okay, I can't see. Oh, you have sent me. Yeah, you've given me the answer. See, now my chat box doesn't pop up when you send a message. So I have to go and open it to see whether you have messaged me. I'm sorry about it. So something is not correct today. I apologize for that. Let me go to the, let me go to this. Oops, not that. Nope, nope. Wrong. Do you see the screen? Do you see solving exponential and logarithmic equations page? Yes, we now Tarinder is asking whether we are going to learn how to differentiate log and exponentials. Yes, we are going to learn that when we come to differentiation, further differentiation under P3. Okay, not under this, under differentiation we will learn that. Can you tell me, do you see the document now? Is that what's appearing on your screen?
Yes, miss. We can see the document, but the black box is covered in.
Right. Okay. Now okay now.
Yeah, now okay.
Right. Okay. So under solving exponential equations, you write what an exponential equation is. You write an exponential equation is when the unknown, that's equation, is when the unknown, that is usually x, is in the exponent, or it's in the power, if that word is more familiar to you. Okay. So whenever your unknown x is in the power of a term, that such an equation is an exponential equation. So you have to kind of bring the x down to solve for it. Okay. But when it comes to very simple equations, your solving is very easy. So I will show you two methods to solve, in which you can solve an exponential equation. Method one. Now you write with me. Method one. You can apply this method one, if your exponential equation has a certain specific format. Okay. If your equation has this format, you can use this method, and you will understand why this method works for such a format. Okay. So let's write the method. Let's say this method. This method requires a very special form of the exponential equation. Write with me. This method requires a very special form of the exponential equation. This method uses the following fact. What is the fact? Oops. If you have some base to the power of x is equal to, let me put a space here, is equal to the same base to another power. If you have an equation in this form, a certain base to some power x equals the same base to some, let me not, okay, wait, yeah, let it be y. So notice that the bases are the same. Then what can you say about the two powers? The two powers have to be the same. This is what we use to solve the equation I just showed on the board. 2 to the power of x is 32. So if you have this, then we can immediately say, oops, we can immediately say that x is equal to y. Now this has to align my alignments. Like that, okay? I will show you an example. Here's an example where we can use this. Example 1. Say you want to solve this. Look at this equation. 5 to the power of 3x is equal to 5 to the power of 7x minus 2. Look at this equation. So it says to solve, okay? You have to solve this. Now, do you see it has that form? You have two terms on either side of your equation. Both terms are power terms, and both power terms have the same base. 5 to some power equals 5 to some other power. Then what can you say? The two powers have to be the same. Otherwise, this won't be true. Because the bases are the same, then the powers have to be the same. So the way to solve this is you can simply write in the next line, using that fact we have written above, you just simply equate the indices, equate the exponents. That is 3x must equal 7x minus 2. And then that's a simple equation. Now you can solve for
X equals to half. X equals half.
to half. X is equal to half. Okay. This also will put here. Align your equal sign. It's difficult for me to do in the document because I'm typing. Here's another example. Example 2. Oops. Example 2. Solve 4 to the power of oops, sorry, wait till I finish typing, because I'm using this equation editor to type. So until I finish typing, you won't see the final thing that I'm, okay? That's 4 to the power of t squared, okay, is equal to 4 to the power of 6 minus t. That's your equation. 4 to the power of t squared, in the power it's t squared, equals 4 to the power of 6 minus t. So this equation again has that special form. You have two index numbers with the same base on either side of your equation. Since the bases are the same, you can say the powers have to be the same. So you simply equate the powers. So you can say t squared must equal 6 minus t. Now that is no longer an exponential equation. You can just solve it now. So that's actually a quadratic equation. What do you get? Um, 2 and minus 3. Okay, yes, Hapsi, that is correct. Oh, there is a question. I'm sorry, Tarinda, I'm just seeing your message now. is, can we prove that ln is the inverse of exponentials like we did for linear expressions? What do you mean by that? How did we prove? What do you mean prove? How did we prove for linear expressions? Then, yes, you can. Yes, you can. Now, Tharindu's question is whether, fine. Now, you know, if I give you a linear function and ask you to find the inverse function of that, you know how to find the inverse function of a linear function. You write the function as y equals blah, 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 and then swap x and y and make y the subject. Remember that procedure that we do? Yes, we can do the same thing. With if I give you a log function and ask you to find its inverse function, you swap x and y and make y the subject, you get the exponential function, and vice versa. It works. You try it. Okay. Right. So
Miss, are the answers for minus 3 and 2?
Minus 3 and 2. Yes. I hope I hope no one needs needs me to show the working here. The rest of the working of how to solve it from this step onwards. It's a quadratic. So I will just tell you what the two answers are. T equals minus 3 and t equals minus 3 or t equals 2. Okay, those are the two answers. So you get two answers here. Right, here's another one. Example 3. Solve three to the power of z equals 9 to the power of z plus 5. What do you think of this? Now, does this have a format for us to
no, but we can turn it.
That's very good, right? It doesn't have the form that we need to apply this method 1. We do have two index numbers, but they don't have the same base. But we can write 9 as a power of base 3. Okay, so we can turn it into base 3. So how do you do it? Now, if you know how, if you can see how to do it, you can do it before me.
3 to the power 2. 3 to the power 2 equals 9.
That's right. So 3 to the power of z equals 9. You can write as, so let me write that in a bracket. I'm writing 9. I'm replacing 9 with 3 to the power of 2 because that is 9, right? And then I have power of z plus 5. So I turn it into that form. Now still it's not in that form. I need to simplify this a little bit. So here you have to apply your rules of exponents. On the left hand side, you have 3 to the power of z equals, on the right hand side, that's a power to a power. You have to multiply the powers. So that gives you 3 to the power of 2z plus 10. I hope that step is clear to you. Power of a power, you have 3 to the power of 2 to the power of z plus 5. Then you multiply the powers 2 times z plus 5. You multiply the powers. Now you have that form. Both terms on either side have 3 as the base, right? So you can equate the powers. So I'm sorry, I have written x for z here. That's z. So z is equal to 2z plus 10. The moment you notice that we have gotten to the same base, one index number with the same base, then the indices have to be the same. And then you solve this. Z is equal to minus 10. Minus 10. Okay, good.
Miss?
Yes, Sarindu?
Miss, for the first example you gave, that 4t squared equals to 4 to the power 6 minus t.
First example, the second example.
Second example, sorry. In that one, Miss, if you had 4 to the power 2 is equal to 4 to the power x squared minus x.
X and t, two unknowns.
No. 4 to the power 2. 4 to the power 2.
2. Okay.
Equals to 4 to the power x squared plus minus x.
Wait, let me write it down. 4 to the power 2 means 64, 16 equals, so that is 4 to the power of 2 equals,
4 to the power x squared
huh?
plus minus x.
Minus x. I hope I
Yeah.
wrote. Let me go to the board and write what you're saying. Is this what you're saying? Okay, wait. You're saying 4 to the power of 2 is equal to 4 to the power of, so this what you have on the left hand side could have been just 16, but you have written it as 4 to the power of 2, and then 4 to the power of, in the power you have x squared. Is that what you're saying?
Yeah.
X squared minus x, like that.
Minus, yeah.
Yeah, okay, then this is in the
Then-
form, then we can equate the powers.
Then miss yeah, okay. I found my mistake. Okay. I thought that we would get 2 answers for the power.
You will get 2 answers for x here. Yeah, so it's a quadratic and you can go ahead and solve that quadratic. Okay, right. Okay, I'm going to go back to the document now. Thank you to whoever who wrote that. Here's your last example under this type. So this method 1 can be applied only if you have this form. Okay, now here's your last example for that form. Example, I think it is example 4. Example 4. Solve, here's your equation. 4 to the power of 5 minus 9x. 5 minus 9x. It's like that. Oops. Sorry. I have to type it in equation mode. 4 to the power of 5 minus 9x. Okay. Equals 1 over, let me finish writing it. After that you copy, because it's not going to look right while I'm typing it. Wait till I, and then 1 over 8 to the power of x minus 2. Copy it properly. So on the left hand side, you have 4 to the power of 5 minus 9x in the power. And then on this side, 1 over 8.
I see where you are going.
Okay, good. Can you try and turn this into our form where we need to have 2 index numbers with the same base so that we can equate the powers? The first step would be to bring this 8 to the power of x minus 2 to the top. So I will let you try it first.
Ooh, this is tricky, but it's easy.
Yes, okay, good. If you get the answer, you let me know.
Miss, is the answer 4 over 15?
Wow, yes, good. Very nice. Good job, Nathan. Others, did you all get it too?
Thank you.
X equals 4 over 15. So let me start working on it slowly. I'm sure you are trying it too. So what I will first try to do is, left hand side, I will write it as it is, 4 to the power of 5 minus 9x. The left hand side term, I'm going to bring that, because the index number is in the bottom. If I bring it to the top, it's going to be 8 to the power of, the sign of the power is going to change. So 8 to the power of
minus x
minus
x plus 2.
So minus x.
Okay.
Yeah, that
right,
will,
okay.
yeah, let me write like that.
Okay.
Like that, right? Okay, so the index, the sign of the index changes to minus. Now, it's little better than how it was, isn't it? So I now have two index numbers, but the bases are different. Here the base is 4, here the base is 8. But you know that 4 and 8 both can be written as powers of 2. So in the next step, I am going to write, I'm going to replace 4 with 2 to the power of 2. That's 4. And then I have 2 to the power of 5 minus 9x on this side, okay? And then I'm going to replace 8 with 2 to the power of 3, because 8 is 2 to the power of 3. Like that. And then to the power of, let me simplify that, minus x, that is, I can say 2 minus x. I hope that is okay if I write like that, 2 minus x. I hope you can follow. Okay. Now, let me simplify this. I have power of a power on both sides. So I can write it as 2 to the, on what is on the left hand side is 2 to the power of, what is that? 2 times 5 is 10, minus 9 times 2 is 18x. Right? Equals, on the right hand side, I have 2 to the power of, what do I have? 3 times 2 is 6, minus 3x. Right? Now I have that form, same base, two index numbers, same base, then the powers must be the same. Now I can, so by you can equate 10 minus 18x to 6 minus 3x. You get, that's just a simple equation and you can solve it. I will just write the answer. You get x is equal to, I'm not showing all the steps. You get x is equal to 4 over 15. Is this clear to everyone? Oh,
Yes.
see, somebody has dropped a message. Yes, Hatsi, you got it too. Okay. Right. Now let's see a second method that you can use to solve an exponential equation. And this method is very useful and more powerful than this method, because this method you can apply only if you have this form. You can have so many equations that cannot be put into this form. But the second method can be used to solve many different kinds of exponential equations, because it uses the fact that exponentials and logarithms are inverses. We bring the x down in this second method. X is in the power in an exponential equation. It's like upstairs, up here. By the use of log, you bring the x down. Okay, that's the technique that we use in the second method. So let us say method 2 and first write it. Let me go to a new page. Method 2. Okay. So basically, what we do in method 2 is, in your exponential function, you get rid of exponential form by taking log, because log and exponentials are inverse operations. When you have an exponent term, when you take the log of that, you can reverse the effect, cancel off the effect, and bring the x down. It's like if you have square root in an equation, you can get rid of the square root by squaring it. Or if you have square, in an equation, if you want to get rid of the square, okay, let me actually show you, because this is not anything new. I always want you to see these connections. Lot of the things that we learn are not like completely new. They are techniques that we have been doing it in other areas. You just might not see it. Like for example, suppose you have an equation to solve where you have come to a step like this. You have square root of x is equal to 6 or something. Okay, now you solve an equation, maybe some equation, and you have come to this step now. Square root of x is equal to 6. Now you're almost there. Solving an equation means to find what x is equal to. You're almost there. You have square root of x is equal to 6. How can, yes, so to get rid of the square root, you square both sides. You have to square both sides. Whoever who put that too, can you, in the red color? Yes, very good. Okay. So because by squaring, you are removing the square root, and then you get x here, and then you have 36 as your answer. Similarly, if you have an equation x squared equals 9, and you want to solve for x, how do you get rid of the square? By square rooting it, right? Thank you. Yes. So you get here x is equal to plus or minus 3, right? So this is not something new. So the same technique we can use whenever we have an exponential function. I will show you an example. Suppose you have 7 to the power of x is equal to 9. Okay. Now, do you recognize that this is an exponential function? How do you recognize that it is an exponential function? Because x is in the exponent. Now, if you think of method 1, can I write 9 as the power of 7? Because I have to change this equation into that form if I am to use method 1. But that it's not going to be easy. I'm sure if you have a log table of base 9, you don't have log tables of base 9 usually. You get log tables of base 10. Or you can maybe use a calculator to see 7 to what power is 9, but that's not going to be easy. We don't have to go into that much of trouble. Very easily, you can bring this x down. That means you can get rid of the exponential form. Because logarithms are inverses of exponential functions, you can actually easily, if you take, because here the base is 7, if you take log on both sides with base 7, this will get cancelled off. Let me show you. Like if you do, like just like earlier, we were, look at this here. We squared both sides, we square rooted both sides, like that. If we take log on both sides here, but you have to know that when you take log, now let me just write here, log, you have to think what base am I taking? So since the base here is 7, if you take base 7, so on the other side also log base 7, 9, okay? So in front you put a log. So you're taking log of these two terms on both sides. Then on this side, this whole thing will get cancelled and you will just get x. Hope you can see it. But we have a little problem here. In your calculators, you don't have the option of, some of your calculators might have this option. But in general, a normal scientific calculator has the log button, that is log 10, base 10, and the ln button, that is log base e. So your calculators usually have log base 10 button and then log base e button. This will look like, I think it will say log on your button, and this will say ln on your button, right? We don't have log base 7 usually in our calculators. So because of that, we don't do this, but we do something similar. I'll go to a new page. Let me write that question again, this equation again. 7 to the power of x is equal to 9 is what I had. This is what you can do. Watch this very carefully and see how powerful this technique is, okay? This is an exponential function, sorry, exponential equation. X is in the exponent. I simply take log on both sides. Log base, what do I take? I take, since the available bases to me in the calculator are log base 10 and log base e, you take one of those. Shall we stick to taking ln all the time? So I'm going to take ln on both sides. See what this enables me to do. I'm going to take ln on both sides. So I'm doing ln of 7 to the power of x and ln of 9. Let me put a bracket so that you can see it easily. It's ln of 7 to the power of x equals ln of 9. Now here this ln and the 7 is not going to get cancelled because they are different bases. They are not complete, they are not inverses now because they are different bases. But does anyone see that there's something that you can do now? Can you go to your log rules? What you have on the left hand side, ln 7 to the power of x, this power on top, remember the log rule? This log rule, this can be brought to the front. See, it's coming down. Okay, this can be written as x ln 7 equals ln 9. Now what is x? X is equal to ln 9 divided by ln 7. The moment you take log or ln, when I say log, can be log base 10 because that's what you have in the calculator, or log any base for that matter. Okay, so we'll stick to taking ln, that is log base e. This works all the time like a charm. So this you can work out in your calculator, ln 9 over ln 7. That is your answer for x. Okay, is this clear to everyone before we write this down?
Perfectly.
Perfectly, wonderful. Okay, so let's write first. You wrote method 2. Let me check the time. I don't want to dig into. We have only 5 minutes. We'll just try to write.
We can do it. We can do
Okay,
it.
we can rearrange it. So let me go to this method 2, and under this, let's quickly write. So you write with me. I will read it out and write at the same time. Write under method 2. When we can't apply method 1, comma, taking log of both sides of the equation allows us to bring the x down. Oops, sorry. Bring the x down and solve the equation easily. Now when I say taking log of both sides, log of some base, okay, but we stick to log base 10 or log base e because that's what we have in the calculator. That's what we can type in the calculator.
Miss, I have a question.
Yes.
Now, Miss, we know how to solve when it is like 7x. No, Miss, like if it's like this, if it's like this, we know how to solve 7x 9. We did that, no, Miss. But what happens? What happens if we have it like this? Minus. Just a rough idea. Just like this.
Yeah. Think about it, Nathan. Still, you can do the same thing. You take log on both ln or log.
So I mean, like, Miss, once I do this, Miss.
Yeah. So this
once I do this, Miss, will it becomes like this, no, Miss? It becomes like this. No, sorry, wrong. It becomes like this, no, Miss?
It becomes x minus 3 times bracket. Put a bracket to x minus 3. It's not x minus 3. Yeah, whole x minus 3 times. Ln 7 equals ln 9.
Equals ln 9, no, Miss?
Then you remove the bracket.
Then each one. Okay. Now, then.
So now you can. I mean, once the x has been brought down, it's a simple equation then.
Okay.
Just remove your brackets and isolate x. Make x an object, right? Yeah.
Understood.
Very good. This method is very powerful. So it's the fact that these two are. It's not even the fact that these two are inverses. We are just using one of the log rules to bring the x down. Right. So example, just copy example 1 and then we can continue. Okay, before that you have solved. Here's the equation. 7 to the power of 9. Sorry, 7 to the power of x is equal to 9. Okay. What you do is, let's take ln. So I'm taking ln 7 to the power of x equals ln, I'm taking ln on both sides, ln of 9. So within brackets here, oops, within brackets, you can write what you have done, taking ln on both sides. That's what you did.
Excuse me, miss. One more thing, miss.
Yeah.
Now we are taking ln, no, miss. We are taking ln. But what happens if we put log?
That is what I explained now. You can take anything. It doesn't matter actually.
Ah, okay. So
Yeah,
basically the bases are the same. The bases are the same.
No. You can take log of log base, log any base. Okay,
Anyways,
let me show
okay.
you. Wait, let me show you.
So basic.
The reason why we don't take log of any base, but we stick to taking log base 10 and log base e is because that's what you have in your calculator. Now let me show you. Now, when you have 7 to the power of x is equal to 9, sorry. 7 to the power of x is equal to 9. Say I take log base, give me any number, base 23. Okay, doesn't matter what you are doing, what base you are taking. Still it works. Does the base matter? Can't we now still apply that rule? We can. The x comes to the front. So it's x log base 23, 7 equals log base 23, 9. And now what is x? X is equal to log base 23, 9 over log base 23, 7. The problem is we can't compute this using our calculators. We don't have log base 23 in our calculator. If we were able to do it, you can take log of any base. Because your calculators only have log base 10 and log base e, that means ln. That's why we stick to taking this or this. That I explained it here. Okay, and I said let's always stick to ln. Let's make it a convention in our class, in our group. Or you can take log base 10. That means just log. Is that clear?
Yeah, miss.
Okay, so you technically you can take log of base anything, any base. And the other thing is, if you take log exactly base 7, like here, you don't even have to. It's just it completely cancels off because they are exactly inverses now. Log base 7 and then base 7 to the power of x. They are inverses now, and then it just goes away, and you just get x. Or even if you don't notice it. Say you don't notice it here. You take base 7 and you don't notice that they're going to cancel off each other because they are inverses. And you bring the x to the front and then x log base 7, 7. You just write it like that. And then on the other side, log base 7, 9. And you know that this is anyway 1. That is 1. So that's just x anyway. So it works with any base. The reason why we stick to log base 10 or log base e is because your calculators don't have other bases, and we will get stuck when we have to work it out in the end. Okay, so you take log here. Yes.
If our calculator has the function which can put the base,
yeah, then you can. I said that too. Some of them might have.
Okay.
Do it.
Understand.
So x ln 7, the x comes in front, then is equal to, I don't know why this is equal to ln 9, and then x is equal to ln 7 over ln 9. Oops. Right? Now that you have to use the calculator and compute it. So ln 7 divided by ln 9. And tell me what the answer is.
1.13.
1.13. Okay. Is this clear to everyone? We will have to do some more lot of examples. This is example 1. We have to practice applying the second method. Did everyone understand?
Yes, crystal clear.
Okay. Anyone else has any doubts, any questions? Any place that was not clear? It's clear. Can I quickly have a response from each person? Then I can make sure that you got it. Put a yes or a no. If it was clear, a yes. If it was okay, Sasindu. Okay. Thank you, Bimandi. Okay, you got it too. Okay, no problem, Sasindu. I know what you meant. Okay, Mihil. Okay, so looks like, okay, Netni. Right, next week, we will continue looking at some more examples and then I will give you a bunch of homework